You know, you might not realize it, but one of the most important shapes in our world is that simple, slanted rectangle, the parallelogram. I mean, it shows up everywhere, from building designs to the way airplanes navigate. Today, we're going to dig in and really unpack the properties that make this four-sided figure so incredibly special and, well, so useful. Let's get right into it.
So, here's our game plan. We're going to start with the absolute basics. What even is a quadrilateral? From there, we'll introduce the star of our show, the parallelogram. And then, we're going to put on our detective hats and actually prove its most important properties. And to wrap it all up, we'll see how all this math helps pilots figure out how to fly their planes. All right, before we can really get into the parallelogram, we need to talk about the family it belongs to. So first things first, let's build our foundation and make sure we're all on the same page about what makes a shape a quadrilateral. At its heart, the definition is super simple, right? It's a closed shape with exactly four sides. I'm sure you can picture a bunch of them right now. Squares, rectangles, maybe a diamond shape. But in geometry, the details really matter. We have to think about how those four sides are arranged in space, which leads to a pretty important distinction. Okay, so look at these two. On the left, we've got a planar quadrilateral. Just think of it like any shape you can draw on a flat piece of paper. All its corners, all its sides, they're all on one flat surface, or plane. But on the right, that's a skew quadrilateral. It's more of a 3D object, where the sides are kind of twisted and don't lie flat. For everything we're doing today, we're going to be sticking with the familiar flat shapes on the left.
All right, so now that we've got our feet firmly planted in the world of flat shapes, it is time to officially introduce the main event, the parallelogram. What makes this thing so special? Well, it all comes down to one simple, really elegant rule.
And there it is. That's the one defining rule. It's not enough for just one pair of opposite sides to be parallel. That would be a trapezoid. Nope. To be a parallelogram, both pairs of opposite sides have to be parallel. This single idea is the master key that unlocks every other cool property this shape has.
So how do we actually know about all these other properties? Well, in math, we don't just memorize rules. We discover them using logic. We are about to walk through a quick, formal proof that takes that one single definition, the parallel sides, and uses it to uncover everything else. It's kind of like being a detective, just following the clues to find the truth.
So here's our mission. We're given a shape, A, B, C, D, and we know for a fact it's a parallelogram. Our goal is to prove that if we slice it down the middle with a diagonal line, the two triangles we create, that's ACD and CAB, are perfectly identical. They're congruent. If we can prove this one thing, everything else will just fall into place.
Okay, let's build our case step by step. Step 1, we're told that ABCD is a parallelogram. That's a given. Step 2 flows right from that. By definition, we know side AB is parallel to side CD. Now for our first big clue, Step 3. See how that diagonal line cuts across those two parallel lines? It creates a sort of Z shape. And a basic rule of geometry says the angles in the corners of that Z, angle 1 and angle 2, have to be equal. We call them alternate interior angles.
And just like that, we're halfway there. Now we just do the exact same thing for the other pair of parallel sides. Step 4, we know side AD is parallel to side BC, again, by definition. Step 5, that same diagonal line makes another Z shape, this time facing the other way. This gives us another pair of equal alternate interior angles, angle 3 and angle 4.
And this is where it all comes together. Step 6 is kind of obvious, but it's important. The diagonal line AC is, of course, the same length as itself. It's the side that both triangles share. So, look at what we've got for each triangle now. We've proven an angle is congruent, a side is congruent, and another angle is congruent. So that brings us to Step 7. The angle-side-angle theorem tells us, without a doubt, that triangle ACD is congruent to triangle CAB. Case closed.
So, what was the point of all that detective work, right? Well, proving those two triangles are identical is the key that unlocks all the other rules of a parallelogram. Let's take a look at the powerful results that come directly from this one proof.
See, because those two triangles are perfect copies of each other, it means all their matching parts have to be identical too. This tells us that side AD has to be the exact same length as side BC, and side AB must be the same as side CD. It also proves that the big corner angles D and B must be equal. These aren't new rules to memorize, they're just logical consequences of the one thing we proved. Okay, now for the really cool part. This isn't just some abstract stuff for a math textbook. These properties are critical for solving real-world problems, especially in physics and engineering. Let's see how pilots use this stuff every single day.
So let's frame this as a question. Imagine for a second that you're a pilot. You know how fast your engines are pushing the plane forward, but at the same time, there's a strong wind pushing you from the side. How in the world do you figure out where you're actually going and how fast you're getting there? Well, the answer is the parallelogram.
Okay, let's map this problem out. We can think of forces like engine power and wind as arrows, which we call vectors. The plane's engine is pushing it straight north at 500 kilometers per hour. At the same time, the wind is blowing it east at 50 kilometers per hour. If you put those two vectors together, they form two sides of a parallelogram. The real question is, what's the actual result of those two forces combined? The plane's actual path across the ground is the diagonal of that parallelogram of forces, and the length of that diagonal is its true ground speed. Using the properties we just talked about and a little bit of trigonometry, you can calculate that the plane's actual speed isn't 500, it's about 505 kilometers per hour. The wind is actually giving it a little boost.
But speed is only half the picture. The direction that diagonal points tells you the plane's true course. It's not flying due north anymore. That wind has pushed it off course. The angle of that diagonal shows us its real heading is now about 6 degrees to the east of north. And trust me, for a navigator trying to cross an ocean, a 6-degree error is a massive deal.
And there you have it. We started with a really simple definition. Two pairs of parallel sides. We used logic to prove its hidden properties, and then we saw how those properties help us figure out something as complex as an airplane's flight path. It really makes you wonder, doesn't it? Where else in the world around us are the properties of a parallelogram hiding in plain sight?